Hello everyone, welcome to this class on finite element analysis, and in this class let's solve this problem on potential energy method. That is, the problem is for the spring system shown in the figure, using the principle of minimum potential energy, determine the nodal displacements. So take F1 equal to 75 newtons and F2 equal to 100 newtons, and the figure is shown here. You can just see in the figure there are three springs, and for each spring the stiffness is given. That is, for the first spring K1 equal to 50 Newton per mm, for K2 is equal to 60 Newton per mm for the second spring, and for the third spring K3 equal to 70 Newton per mm. And deflection is given. Delta 1, delta 2, delta 3 are nothing but the deflections at each spring, that is compression or extension of the spring. And U1 is the displacement for this entire system, and U2 is the displacement for this at this node. So at these two nodes you have displacements u1 and u2. That is, I'll just name these nodes as 1 and 2. Therefore the displacements is 1 and 2, and force is applied over here. The F1 force is applied over here and F2 force is applied over here. F1 force is applied at node 1 and the force of F2 is applied at node 2. Okay, now let's try to solve this problem. So the solution for this problem is the potential energy functional PE functional is given by strain energy SC plus work potential WP. So strain energy is given by strain energy for a spring. Strain energy for every spring problem, it's given by half K delta square. Half K delta square, where K is the stiffness and delta is the deflection. And as there are three springs over here, the answer will be strain energy for the whole system. Strain energy for the whole system, you can just write it as half K1 delta 1 square plus half K2 delta 2 square plus half K3 delta 3 square. So this is the strain energy for the entire system, because as there are three springs, there will be three stiffnesses and three deflections. Similarly, you have work potential. Work potential for the whole spring or the whole system, or generally work potential is given by minus F into U. And here in this problem, work potential for the whole system, you can just write it like, as there are two displacements and two forces, you will just get it minus F1 U1 minus F2 U2. Now let's try to combine both. So let me just try to highlight this so that you will get to know it better. So this is strain energy and this is work potential. So now let me try to combine both. So now you have half K1 delta 1 square plus half K2 delta 2 square plus half K3 delta 3 square. So this is nothing but the strain energy for the entire system. Now minus F1 U1 minus F2 U2. F1 U1, F2 U2 are nothing but the work potential for the entire system. Now I have to replace this delta 1 with these displacements. Delta 1 deflection is nothing but the displacements. So whenever a force is applied at node 1, there will be a displacement in this system. So delta 1 equal to the displacement on the right minus the displacement on the left. On the right there is a displacement u1. You can just see here on the right from this node there is a displacement u1, and on the left of d1 there is the left of delta 1 there is no any displacement at all. Therefore delta 1 equal to u1 minus 0, which is equal to u1. And delta 2 is nothing but the same thing. Delta 2 also experiences on the right you have displacement u1 and on the left you don't have anything. Therefore it will be u1 minus 0, which is equal to u1. Therefore delta 1 equal to u1 and delta 2 also will be equal to u1. And what about delta 3? Delta 3 is nothing but the displacement on the right side. Displacement on the right hand side is just shown in the node 2, that is displacement u2, and on the left hand side you have u1. So u2 minus u1, right hand side minus displacement minus left hand side displacements. So now let's try to substitute this delta 1, delta 2 and delta 3 in this equation. In this, so let's say let me call this let me even highlight this also. So let me try to say this as equation number 1, substituting the above in equation number 1. So what do we get whenever we substitute that? So we get pi equals to half K1. So let me first write that that equation, half K2 delta 2 square plus half K3 delta 3 square minus F1 U1 minus F2 U2. And also let me write this once again, delta 1 equal to U1 and delta 2 equal to U1 and delta 3 equal to U2 minus U1. So on substituting, what do we get? We get pi equal to half k1. In place of delta 1, I'll just write it as u1 square plus half k2. In place of delta 2 also, I'm going to write it as u1 square plus half k3. In place of delta 3, I'm going to write it as u2 minus u1 the whole square minus f1 u1 minus f2 u2. So now let me try to simplify this equation. So half k1 u1 square plus half k2 u1 square. So now let's try to simplify this. In this is similar to the equation a minus b the whole square. That is a square minus b, a square plus b square minus 2ab. So u2 square plus u1 square plus 2 u1 u2. So that is u2 square plus u1 square minus 2 u1 u2. And this is going to be minus f1 u1 and this is going to be minus f2 u2. So next thing what you can do is let's try to multiply this half k3 inside this bracket. So it's going to be half k1 u1 square plus half k2 u1 square plus half k3 u2 square plus half k3 u1 square. And when this half and u2 gets multiplied, 2 and 2 gets cancelled, then plus into minus will be minus. So it will be k3 u1 u2. And this is going to be minus f1 u1 and this is going to be minus f2 u2. So this is going to be pi. So this is the final equation of pi after simplification. Now what you have to do is, for this potential energy to be minimum, for PE to be minimum, dou pi by dou u should be equal to 0. Dou pi by dou u should be equal to 0. So u is nothing but displacement. So in this problem we have two displacements, u1 and u2. Therefore dou pi by dou u1 and dou pi by dou u2 both has to be equal to 0. So whenever you partially differentiate this with respect to u1 and u2, you have to get the answer as 0. So dou pi by dou u1. So let's try to partially differentiate this equation with respect to u1 first. So whenever I'm trying to partially differentiate with respect to u1, wherever you have u1 variable, only that will be considered as variable, and wherever you don't have u1 variable, that will be considered as constant. So in this term, half k1 will be considered as constant. Partial differentiation of u1 square will be 2u1. And similarly here, half k2 will be considered constant and differentiation of u1 square is 2u1. And here the entire term will be considered to be 0 because there are no any u1 terms. And here it is going to be half k3 and u1 square differentiation is 2u1 minus here k3 u2 will be considered as constant and u1 differentiation is 1. And here f minus f1 and that is going to be equal to 0. So now let me try to equate it to 0 and let me try to cancel this all these. So finally what I'm going to get is k1 u1 plus k2 u1 plus k3 u1 minus k3 u2 minus f1 equal to 0. Now what I'll do, I'll just take u1 common over here. So I'll get u1 into k1 plus k2 plus k3 minus k3 u2, that is equal to, let me just send this f1 to that side, I'll get this. So this one, let me take it as equation number 2 and let me try to highlight this answer as well. And next thing is, I'm going to do partially differentiate that equation with respect to u2. So when I try to partially differentiate that above equation with respect to u2, now only u2 has to be a variable. So wherever you find u2, that has to be, that will be considered as variable, and wherever you find u1 or some other thing, that will be considered as constant. So the first term doesn't have any u2 variable in it, therefore it will be considered to be constant. So 0 plus second term also doesn't have any u2 variable, so that will also be constant. Third term has u2 variable, therefore half k3 and u2 square differentiation is 2u2. And fourth term doesn't have any u2 variable in it, therefore that will also be considered to be a constant, so the differentiation will be 0. And fifth term, it will be minus k3 u1 and differentiation of u2 will be 1. And sixth term, it doesn't have any u2 variable, therefore it will be 0. And seventh term, it's going to be minus f2 and that will be equal to 0. So now when I try to simplify this, I'm going to get k3 u2 minus k3 u1. So if I just send this f2 to that side, it's going to be plus f2. So now I'm going to write this as minus k3 u1 plus k3 u2, or else let me try to leave it as it is. So now I'm going to take it as equation number 3. So now what I'm going to do is just going to equate this to K3U2. K3U2 equal to F2 plus K3U1. F2 plus K3U1. And this I'm going to substitute it as, this I'm going to consider it as equation number 4. Now substituting equation number 4 in equation number 2, we get, so just substitute this equation here in place of minus K3U2. I'm going to substitute this. So therefore I'm going to get U1 into K1 plus K2 plus K3 minus, and in place of K3U2 I'm going to substitute F2 plus K3U1. That is going to be equal to F1. So the next step is, after this what I'm going to do, let me just try to rewrite this equation over here. So it is going to be U1 into K1 into K1 plus K2 plus K3, K1 plus K2 plus K3 minus F2 plus K3U1 minus F2 plus K3U1, that will be equal to F1. So now let me try to equate it. So now what I'm going to get is, so let me try to even substitute, multiply this U1 inside, U1 plus K1 plus U1 plus K2 plus U1 K3 minus F2, and this minus, if it gets here, I'll get minus U3 K1 U1, that is equal to F1. So already we have K3 U1 and K3 U1. So minus K3 U1 and plus K3 U1. U1 K3, K3 U1, everything are same. So this and this gets cancelled, and this minus F2, if it goes to the other side, it's going to be plus F2. U1 K1 plus U1 K2, that is going to be equal to F2 plus F1. So now here I'm going to take U1 as common, therefore I'm going to get K1 plus K2, that is going to be equal to F1 plus F2 or F2 plus F1. Therefore U1 equals to F1 plus F2 divided by K1 plus K2. So now let's try to substitute this value. So F1 we have considered to be, we have taken it as 75 Newton, F2 is considered as 100 Newtons. So it is considered in the question itself. So 100 and 75. So 75 plus 100 divided by K1 and K2. K1 is considered to be like 50 and K2 is 60. So 50 plus 60. So U1 is going to be, so 175, let me just use the calci. So 175 divided by 110. So the answer is going to be 1.591 mm. So let me just try to round it off the answer, and let me try to substitute this U1 into any of the equations so that I'm going to get the answer. So let me just try to use some equation. Let me try to use this equation itself, like K3U2 minus K3U1, that is equal to F2. So K3 is found to be how much in the problem? It's found to be 70 into U2 minus 70 into 1.591, that is nothing but equal to F2, and F2 is considered to be 100. So 100. So now let me try to solve this. So 70 U2 is equal to 100 plus 70 into 1.591. So 1.591. So 100 plus 70 into 1.591. So the answer is found to be 211.37. So that is nothing but 70 U2, and thus U2 equal to 211.37 divided by 70. So upon division by 70, I'm going to get it as 3.01. So 3.01. Therefore U2 is 3.019 mm. So therefore we have got the answers finally. U1 is 1.591 mm and U2 is 3.019 mm. So we have obtained both the nodal displacements at nodes 1 and node 2. We have just got those answers. Okay, thus we have obtained all the answers. U1 is 1.591 and U2 is 3.019. So they are nothing but the displacements at node 1 and node 2. I hope you have understood this problem. Thank you so much. Bye.